Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chaturji, and a warm welcome back to my channel. Welcome to today's DIY Excel project. Before we dive in, a quick note for my non-civil engineer viewers. While we'll be tackling some technical concepts today, please feel free to follow along. Simply treat the engineering terms as numbers and focus on applying the Excel process to your own DIY spreadsheet projects. In my last 3 videos, we thoroughly covered the theoretical aspects and the design of a doubly reinforced beam for bending stress and shear stress. We first covered this through a detailed PowerPoint presentation and then applied it in Excel. Today's video, titled Deflection Check in Doubly Reinforced Beam IS-456 Part-04, is an Excel presentation and a perfect DIY project, especially for my fellow civil engineers. Catch up on the series. If you're new to the channel, I highly recommend checking out Part 1 to Part 3 of the series first. And for an even stronger foundation, my IS-456 singly reinforced beam design, bending moment, shear force and deflection limits and checks in Excel series, Parts 1 through 7, will be incredibly helpful. In this episode, we're going to dive into several critical aspects of deflection check for doubly reinforced beam in Excel. To help us visualize the tasks ahead and recap the necessary steps for deflection check, we'll start by looking at the similarities and differences in deflection check between singly and doubly reinforced beams. Let's now move to our next slide. Alright, so picking up from our last point, let's dive into the similarity in deflection check for both singly and doubly reinforced beams. This is crucial because many of the foundational principles apply to both types of beams. As per IS 456:2000, Clause 23.2, we have general principles for deflection check that are applicable to both singly and doubly reinforced beams. The very first, and often initial, check we perform involves the limiting deflection ratios. The IS code specifies basic span to effective depth ratios based on different support conditions. These are: for a cantilever beam, the ratio is 7. For a simply supported beam, it's 20. And for a continuous beam, the ratio is 26. Now, an important note here: for simply supported and fixed beam spans greater than 10 meters, these basic values, that is, 20 and 26, need to be multiplied by a factor of 10 divided by the actual span in meters. Furthermore, and this is critical, for cantilever beams with a span greater than 10 meters, a full, actual calculation for deflection is explicitly required. You can't just rely on the modified ratio, you must perform a detailed deflection calculation for cantilever beams. These ratios are your first line of defense in ensuring deflection limits are met. Let's move on to the next aspect. Now that we've covered the similarities, let's move on to the differences in deflection check for singly and doubly reinforced beams, specifically focusing on the modification factors. This is where the critical distinctions really come into play. The basic effective span to effective depth ratios. Those L effective by D effective ratios we just discussed are further modified by specific factors to account for the characteristics of the beam. Firstly, for singly reinforced beams, the modification factor is often denoted as KT. This factor considers the area of tension reinforcement, AST, along with the value of Fs, which is the service stress in the steel. Now, if you're new to my channel and interested in a deeper dive into the modification factor for singly reinforced beams, I highly recommend following my singly reinforced beam design series. This factor, KT, fundamentally accounts for the amount of tension steel provided. Generally speaking, providing higher tension steel leads to stiffer beams, which in turn allows for higher permissible span-to-depth ratios. You can find the specific curves and values for this in Figure 4 of IS 456, 2000. And here's where the primary difference for doubly reinforced beams truly lies, the modification factor related to compression reinforcement. This factor is often denoted as Kc, and it directly depends on the area of compression reinforcement, ASC. The presence of compression reinforcement plays a significant role in reducing creep and shrinkage deflections, and it directly increases the overall stiffness of the beam. This allows for more slender sections without exceeding deflection limits. For the details on this, we will need to refer to Figure 5 of IS 456, 2000. So, while the initial ratios are the same for both types, the presence and amount of compression reinforcement introduce a crucial modification that differentiates the deflection check for doubly reinforced beams. Let's break down these factors in even more detail as we proceed. To tie everything together, let's look at this summary table, which clearly outlines the key features and differences in deflection checks for both singly and doubly reinforced beams. This will serve as a quick recap of what we've discussed and what's crucial to remember. First, let's consider reinforcement. In a singly reinforced beam, reinforcement is, as the name suggests, only in the tension zone, indicated by AST. Conversely, for a doubly reinforced beam, we have reinforcement in both the tension, AST, and the compression, ASC, zones. Next, looking at stiffness. Singly reinforced beams generally exhibit lower stiffness, particularly when subjected to sustained loads. Doubly reinforced beams, on the other hand, have higher stiffness, especially under sustained loads, primarily due to the compression steel resisting creep. Moving to the ICR calculation, or the cracked moment of inertia calculation. For singly reinforced beams, this calculation considers only the tension steel's transformed area. But for doubly reinforced beams, it considers the transformed areas of both tension and compression steel. This is a significant difference. Then we have the modification factor for ASC. For singly reinforced beams, this factor is not applicable, or you can consider KT as 1.0 in this context as there's no compression steel to modify for. However, for doubly reinforced beams, this factor, Kc, is applicable. It's obtained from Figure 5 of IS 456:2000 and is typically greater than 1.0, effectively increasing the permissible span-to-depth ratio, L/D. Finally, let's look at their primary use. A singly reinforced beam is typically used where the concrete section alone is sufficient to resist the compression forces. A doubly reinforced beam is employed when the beam depth is restricted, or specifically to reduce long-term deflection, or in situations involving moment reversal. This table clearly highlights why understanding both types is essential for efficient and compliant design. With this summary, we're now ready to move into the preparation of Excel application of these principles. Alright, let's now move towards the calculation for the value of KC. The title of this slide is clear: Steps for the calculation of modification factor KC for doubly reinforced beam. As you can see on this slide, we have two important graphs. On the left-hand side, we have figure 04, which we use to determine the value of KT for singly reinforced beams. On the right, we have figure 05, which is specifically for finding the value of KC for doubly reinforced beams. For our discussion today, we will concentrate our focus primarily on figure 05. To me, this figure is conceptually simpler to interpret than figure 04. In figure 05, the percentage of compression steel, PC, is plotted along the x-axis, and the corresponding KC factors are plotted along the y-axis. On a closer look at this figure, you'll find that the range for PC is from 0 to 3%, and the range for KC is from 1.0 to 1.5. This KC is simply a multiplier, it has no unit. The nature of this graph is not a straight line, but a curve. Ultimately, we need to find the appropriate value of KC from this curve. This KC value then has to be multiplied with the basic effective span to effective depth ratios, those L effective by D effective ratios we discussed earlier, to obtain the final, modified effective span to effective depth ratio. Therefore, we can state the relationship as effective span to effective depth ratio equals to KC multiplied by basic effective span to effective depth ratio, which implies effective span equals to KC multiplied by effective depth. If we find that this calculated effective span is greater than or equal to the actual effective span of our beam, then and only then can we say our deflection check is okay. Otherwise, we will have to alter our design parameters to satisfy the deflection criteria. Now, the crucial question is, how can we find the value of KC in our Excel sheet automatically? Now, here is the solution to our question: how can we find the value of KC in our Excel sheet automatically? To achieve this, I initially considered developing a complex formula by reverse engineering the curve with the help of Gemini AI, as usual. However, Gemini AI wisely suggested adopting the standard linear interpolation method. This is because for our practical engineering purposes here, we need to extract an approximately close value of KC, not necessarily an exact, precise mathematical fit for the entire curve. And, once again, in my life, other than my close family members, you, Gemini AI, are the first person providing such valuable cooperation and suggestions, free of cost. Thank you, Gemini AI. Now, let's discuss the philosophy behind interpolation. We know that a small segment of a large curve can be closely approximated as a straight line. Based on this fundamental principle, we are going to extract the value of KC from figure 05. In the actual graph, figure 05, you'll observe that the interval for PC is 0.5%, and the interval for KC is 0.10. However, for more accurate, closer values of KC in our calculations, we need to consider smaller intervals. Look at the table at the top of the slide. Here, we've broken down these intervals. You can see the PC interval is now 0.25%, and the corresponding KC interval is roughly 0.025 or 0.05, depending on the segment. This refined table directly translates points from figure 05 for precise interpolation. Let's take an example. Say, we've calculated the value of PC as 1.12%. This value falls as an intermediate point between 1% and 1.25% for PC. The corresponding KC values for these points are 1.25 and 1.30, respectively. Notice how these specific cells in the table are highlighted with different colors. We'll define these points. Let's call 1% PC down, and 1.25% PC up. Similarly, for KC, 1.25 is KC down, and 1.30 is KC up. Now, let's calculate the differences. PC up minus PC down, equals 0.25. And, KC up minus KC down, equals 0.05. We then calculate the increment in KC for a unit increment of PC. Let's call this I. Therefore, I equals 0.05 divided by 0.25, which gives us 0.20. To get the final value of KC for our given PC of 1.12, we use the linear interpolation equation. KC equals to KC down plus PC minus PC down, multiplied by I. Plugging in our example values, KC equals to 1.25 plus 1.12 to 1.00, multiplied by 0.20. This calculates to 1.274. The beauty of this method is that Excel will perform this entire calculation automatically. So, for any calculated value of PC between 0 and 3%, our Excel sheet will find the correct KC value automatically, just by applying this interpolation logic. Alright everyone, we are now literally at the doorstep of our Excel sheet for the demonstration of the deflection check for doubly reinforced beams. You might recognize this image. It's a snapshot of the final slide from our last Excel presentation, where we thoroughly demonstrated the shear stress calculation for doubly reinforced beams. It serves as a reminder of the practical application we're building towards. Now, since you've stayed with me and are watching this video right up to this point, I have a sincere question for you. I truly value your honest feedback. Is this presentation good, or bad, or, dare I say, worst? Please, take a moment and write your thoughts in the comments section below. Your feedback is invaluable to me. And while you're there, may I ask for a small favor? If you are new to my channel, or if you've been watching my videos without subscribing, please consider subscribing right now. And don't forget to turn on the notification bell so you don't miss any of my upcoming content. If you are already a subscriber, please don't forget to like this presentation if you found it helpful. Or, if you dislike it, please do so, but please accompany it with a comment explaining why. If you dislike this presentation without any explanation, it will feel like a punishment offered by you, the judge, without judgment. Your constructive criticism truly helps me improve. Indirectly, It will be helpful to you also, as it helps shape future content. And finally, if possible, please share the link to this video among your friends and fellow engineers. Your support and engagement will hugely motivate me to hit my next big target, which is an exciting series on STAAD Pro operations. And, before we dive into Excel, don't forget to watch this entire video to grasp the full picture of the deflection check. To feel the magic of logic, let's move on to the actual Excel sheet. Now we are on the actual Excel sheet, and we are observing the same sheet where we finished our last tour. Today our first task is to construct cell that will notify us regarding the completion of the design. For that, I have selected the cell, H1, beside the heading, 02 Doubly Reinforced Section. Now, I am selecting the formula from formula box for cell, H1. In the formula box we are seeing, formula for the notification for the completion, equals to if, open parenthesis for if function, n, open parenthesis for n function, check underscore 03, equals to, OK, in quotation, comma, SV, greater than, 0, comma, check underscore 04, equals to, OK, in quotation, close parenthesis for n function, comma, OK, in quotation, comma, blank quotation, close parenthesis for if function. Simple meaning of this formula, if r check underscore 03, that is check for bending stress is OK, and SV, spacing of the stirrups is greater than 0, SV, greater than 0, is the symbol of the successful completion of the shear design of the beam, and check underscore 04, that is check for deflection is OK, then Excel will tell us OK, that means all the checkpoints are OK, hence our design is completely OK. I have written this formula in the cell H1. Presently the cell is blank, because our design need to check the deflection. In this sheet, we have another, hidden table below the table, with heading, shear stress calculation. And heading of that table is, deflection check and limit for beams. Now I am unhiding the table with deflection check and limit for beams. Presently, this table is blank, because we have not selected any beam type, and the dimensions of the beam. Here beam type means, 1. Cantilever, 2. Simply supported, 3. Fixed beam and dimensions means length, L, and support widths, B_1 and B_2. Actually the calculation for deflection, will be done on the sheet, named as, deflection calculation, and on this table. Heading of this table is, table for the calculation of deflection for singly and doubly reinforced beam, and the calculated value we have to transfer, to the sheet named as design_01. For the same reason, presently this table is blank. Now, I am returning to the sheet, design_01. Before bringing the datas for deflection, we need to make redundant the heading FS, and its value, in cell G17 and H17, respectively, during the deflection check for doubly reinforced beam. You may ask, why? This is because for deflection check in doubly reinforced beams, exhibiting the FS value is little bit irrelevant. Now, I am selecting the formula for heading of FS, from formula box. Now, we are seeing a formula in the formula box, and formula for heading of FS, that I typed in cell A is G17. Equals to, if, open parenthesis for if function, design underscore code, equals to, 2, comma, blank quotation, comma, within quotation, fs equals to, close parenthesis for if function. By the help of this formula, we are instructing the Excel, if our design code is design underscore code, equals to, 2, that is the design for doubly reinforced beam, don't display the heading, FS, or keep the cell G17, as a blank. Formula for the value of the FS, that I typed in the cell, H17 is, equals to, if, open parenthesis for if function, design underscore code, equals to, 2, comma, blank quotation, comma, if, open parenthesis for if function, n, open parenthesis for n function, design underscore code, equals to 1, comma, check underscore 03 equals to, OK, within quotation, close parenthesis for n function, comma, round, open parenthesis for round function, 0.58, multiplied by fy, multiplied by, pt underscore req, divided by pt underscore prov, comma, 0, close parenthesis. For round function, comma, blank quotation, close parenthesis for intermediate if function, close parenthesis for overall if function. Simple meaning of this formula is the combination of two if function. In first if function says, keep the cell blank, if the design underscore code is 2. That is for doubly reinforced beam. Second if function says, if the design underscore code is 1, and check underscore 03 equals to, OK, that is for singly reinforced beam, and finished his calculation for bending stress successfully, then calculate the value of Fs, by the help of this formula, 0.58, multiplied by Fy, multiplied by, pt underscore req, divided by pt underscore prov, and convert that value to a whole number, otherwise, keep the cell blank. Since we are presently designing the doubly reinforced beam section, these two cells are blank. They will become prominent when we calculate the singly reinforced beam section. In our previous video, Excel for IS-456 beam design deflection limits and checks, Part-05, we discussed the concept of effective length for deflection checks. Today, I want to present a brief corrigendum, or clarification, to ensure our calculations are in full compliance with IS-456:2000. In this slide, you are seeing the explanation of effective length that was presented in my previous video. Please note, this is not the exact explanation as per IS-456:2000, and it has since been updated. Now, let's move on to the correct explanation for effective length for simply supported and fixed beams, as per IS-456:2000. Here, we are seeing the updated effective length calculations for simply supported and fixed, or continuous, beams. As per IS-456:2000, the effective span for deflection for these types of beams is the minimum of two values. First, the clear span plus the effective depth. And second, the center-to-center distance of supports, which is calculated as the clear span plus half the sum of support widths. This formulation precisely captures the code's requirements for these beam types. Now, let's move to the next slide, for the effective length clarification specifically regarding cantilever beams. In this slide, we are looking at the effective length for cantilever beams, where there was a key point needing clarification. As per IS 456:2000, clause 22.2, b, the rule for a cantilever is precise and depends on its context. On the left, we have the case for a standalone cantilever beam, meaning it's not part of a larger continuous system. Here, the effective length is taken as its clear span plus half the effective depth. There is no minimum of comparison, it's a direct calculation. On the right, we have an important exception: if the cantilever forms the end of a continuous beam, acting as an overhang, then its effective length is taken as the clear span plus half the width of that particular support. Once again, there is no minimum of comparison, it's a direct calculation. This distinction is crucial for precise deflection calculations in accordance with the code. Please ensure you apply the correct effective length based on whether your cantilever is standalone or an overhang of a continuous beam. I have made the necessary adjustments in our Excel sheet accordingly. After a long and fruitful discussion with Gemini AI, we came to this logical conclusion. So, once again, thank you, Gemini AI. Let's move to the Excel sheet once again. Now, once again we are on the dashboard. First I will demonstrate the dynamic heading for modification factor. To do that I am selecting the formula number 04. The formula for the heading of modification factor is equals to if open parenthesis for if function n open parenthesis for n function check underscore 03 equals to OK, comma, design underscore code equals to 1, comma, beam underscore type greater than 0, close parenthesis for n function, comma, within quotation, modification factor, k underscore t, comma, if, open parenthesis for if function, n, open parenthesis for n function. Check underscore 03 equals to, within quotation, OK, comma, design underscore code equals to, 2, comma, beam underscore type greater than, 0, close parenthesis for n function, comma, within quotation, modification factor, kc, comma, within quotation, modification factor, close parenthesis for first, if function, close parenthesis for second if function. Simple meaning of this formula is, if, check underscore 03 equals to OK, and design underscore code equals to 1 and beam underscore type, greater than 0, that means we have selected a beam in the cell, with heading, beam type, then heading of the modification factor, will show, modification factor, k underscore t. Similarly, if, check underscore 03 equals to OK, and design underscore code equals to 2 and beam underscore type, greater than 0, it will show, modification factor, kc. Otherwise it will show a simple heading, modification factor. Presently, since we have not selected any, beam type, we are seeing the heading, modification factor. Alright everyone, let's take a quick break here. In our next episode, we'll dive into building the Excel table for our deflection check in singly and doubly reinforced beams. It's going to be a dynamically interchangeable sheet. Your free Excel sheet is here. Now, for something many of you have been eagerly awaiting, the free Excel sheet I demonstrated previously, the one without the detailed Excel explanation. I've been thrilled by all your fantastic emails, and I'm genuinely excited to share it with you. To get your copy, please read the instructions carefully in the description below this video. It's a quick, two-step process. You'll need to email me your request and leave a comment on this specific video letting me know you've sent it. Both steps are absolutely essential. Once you've got the file, a quick "got it" or "thank you" in the comments would truly make my day. Empower your learning. Throughout this entire beam design series, my main goal is to empower you to build your own Excel sheet. Relying solely on pre-made sheets can limit your understanding. Developing your own truly builds your skills and confidence. If you hit any snags while creating your sheet, remember, I'm here to help you completely free of charge. My focus is always on your learning and skill development. Support my work. If you'd like to support what I do, here are two simple ways. Watch my videos in full. Consider a contribution, whatever fits your budget, without any pressure. You'll find the details in the description, and the communication process is the same as requesting the Excel sheet. Your engagement genuinely helps me improve how I share knowledge with all of you. Stay engaged and support the channel. I hope you enjoyed this episode. Please leave your feedback and questions in the comments below. If this video helped you, give it a big thumbs up. Remember, sharing knowledge means enhancing knowledge, so please share this video. And if you want to support my honest effort, subscribing to the channel is the best way to do it. Let's grow together. Thanks for your cooperation and support.